Yeah, Chandan, you can address me as Vivek. Okay, no sir or anything else. Yeah, good evening. Okay, we'll wait till 4:05. It's 4:01 now. Um, Chandan, did you get a chance to go through the lecture this week from the NPTEL? Yes, okay. Uh, Perfect. So I guess week 11 and content before that, week 10 and week 9, they must be clear. This is not heavily dependent on those week. I mean, content of those week, but they do, share some similarities when it comes to Markov localization. There is nothing but base filter, like we had back then in, I guess, week 8 or week 9. Yeah. So yeah. So now, so last week we had occupancy grid mapping where we did position localization in a local sense rather than a global positioning. We You can do global positioning. We did local positioning there using the features that were made in the occupancy grid mapping. So today we'll be learning how to navigate through those kind of maps, or say any existing terrain that we know for static environments. So I'll be discussing what is these terms like static or something like that. Um, yeah, so we'll wait for another 2 minutes, and probably after that we'll get started. Yeah. So please raise a hand because sometimes I don't get the feedback of voice. So please raise a hand if you have any questions. I'm dialing in from two system. One system records the entire session. The other use it for writing. Um, yeah. So the one that is recording the session, in that I can have your audio or something like that, and I can also see your questions without moving away from notebook the notebook we are in. Yeah. It's okay. It's almost 4:05, so we'll get started. So what we mean by localization is knowing where we are, right? It's something like okay, it's a full stop or exclamation, knowing where we are. Yeah, so that is what localization means. When we say something is foreign or global, or something that is, yeah, well, let's take the word foreign. What we say with that is that it is not part of where it is. It is rather away from where uh, we are taking as the local space from which we derive that definition. So localization means that you are getting familiarized in that local space. It's something like that. So boiling it down, it would be something like knowing where we are, right? So in this, the first thing that will come to your mind is the position. That is, say, in your 3D 3D Cartesian space, you will have x, y, z, or you can have something like x, y, z, r theta, r yeah, sorry, theta x, theta y, theta z. Okay, you can omit this, but then yeah, let's just keep it for comprehensive content. Yeah, x, y, z, and theta x, theta y, and theta z. These are all your. This is your position. This is your pose, right? So a localization means that I have information of these, right? We will restrict our discussion till X, Y, Z, or we would assume that the robot is a point for now, for all this breadth first search. We'll assume robot is a point, right? So in position tracking, there can be two ways of tracking your position, right? So when we say a track or tracking, we are inherently invoking something called trajectory or the history, right? That's called keeping something in track, right? Now when we are looking for position tracking, right, there are two things that come to our mind. One is local, another is global. This is something like, where do I stand with respect to something, right? And global is, where do I stand irrespective of multiple things, right? So this is the difference between a local and a global position tracking. So yeah, again here you can see that when we are dealing with non-deterministic tracking, something like that we have in our hand nowadays, that we do not know where the robot is with a deterministic value, like we are not sure where the robot is because of two things. One, probabilistic nature of the position, right? That is what we dealt in base filter, that is position of the new state given your control and the position of the previous state, right? So the probability of the position and the probability, not possibility, it's probability of your sorry, yeah, probabilistic nature of your measurement, right? That is nothing but probability of zi given xi minus 1, right? So these are the two probability that is playing, and hence these local and global positioning again become probabilistic. And due to this probabilistic nature, we can have something like Kalman filter here, right? Extended Kalman or particle filter, where multiple hypotheses can be um, administered, right? So these all have a Gaussian distribution, right? Like last assignment, you would have probability of the error in the position being zero with some variance, right? The mean of that error being zero or near zero or something like that, with certain variance. That variance we were controlling by alpha 1 and alpha 2 and so on, because of multiple other like odometric model or velocity model. We had different factors that were contributing in the variance. This probability, what I mean, is a normal distribution, yeah, with the mean being zero. This is nothing but the error in the position, right? And with some variance, okay. So this is what we can incorporate in a local positioning system, yeah. And same holds for global positioning, global tracking, right? Now we'll get into a environment where we talk about environment, that is static positioning versus dynamic, Right, let me positioning here. Right. What we mean by static is that the robot is not static, rather the environment is. Right. So you have a bunch of obstacles, and you have your robot, and this domain. Yeah, this domain is also fixed, right? And with dynamic, we say that the environment is also moving. Is moving, right? Static. So what we mean by this is that these obstacles can move, collide, form new obstacles. This domain space can increase. So what you require in situation where it is dynamic. Yeah, let me just write it. Dynamic. In dynamic, you would have you would require simultaneous, or if not simultaneous, periodic localization and mapping. Right. So you need to define your map again and again as your environment keeps changing. Right. For a static environment, this mapping needs to be done maybe once or not at all if the map is already known. And in static, even you have to do localization, which will be simultaneous, which will update as you give a control signal UI. Right. So every time you will have a belief, prediction, and then a belief. Right. Your belief prediction will be an integral probability of the new state given psi. Yeah. Xi over all states. Yeah. Xi minus 1. Xi minus 1. Yeah. And your belief will be with respect to your belief prediction, right? New times of probability, then I divided by xi. I may have messed up the formula or something. You can check it once. Let me do that. I think I don't have that note with me, but anyway. Um, yeah, state probability, assume Markov property, belief. Yeah, yeah, I missed this one. Belief will be here, or else it will become independent of it. Right? And your belief will be nothing but new times of this with belief prediction. Yeah. Right? Yeah, I've missed the belief term. Okay. So what we are doing is essentially this with our localization. So you have your Markov localization, which depends on something like this. So now we'll move forward to something called active and passive localization. I think we can address it here. What we mean by active localization is that your the localization, or let's take the element that you are localizing, the things that are sensing the measurement, right? They are static. That would mean a passive localization, and versus an active, like your robot itself is moving with a sensor attached on it. This will be an active localization, right? So these are some basic terminology before we move ahead. So yeah, so now we would deal with something called path planning. There's an N here. Yeah, path planning. So what we mean by path planning? So let us debate about some terms. One is called trajectory versus path. Right. A trajectory has an information of how it needs to go, like it has a path, and on that path how it needs to go. That would be a trajectory. Something like it has data of x, y, z where it needs to go, and on those points what would be the velocity, acceleration, and let's take even maybe jerk and snap, something like this. There are minimum jerk trajectories for when you take armed robots. They have minimum jerk trajectories so that the jerk on the links are not there. There are when you have something like a quadcopter or something like that, you would have something called minimum snap trajectory, right? So that is what we mean by trajectory. And a path means how you need to go from A to B, right? A path can be something like this, something like this, something like this, something like this. The famous problem that we can pose here is, let's take, you have a point from where you drop a ball. Okay, G is acting downward, and you have another point here, and you are asked to make a path or make a sliding surface that the ball would take to reach B in the least time, right? This is minimizing time of travel problem. This is called the Brackestone's problem. This was solved by many people. To name few, Bernoulli attempted it. Newton also attempted it, and they get to a solution where we have integral the time that is taken over this path. Yeah, no, we get time which is integral v yeah that's right, v ds by v. Yeah, so we minimize this functional, right? Not a function, it's a functional, right? So this is a famous problem that this is the path, that this path will be a cycloid, right? So yeah, it will not be a straight line, it will rather be a curved one. Okay, so now these are not in the topic of our interest. What we will be dealing with is breadth first search, right? In that we'll have before I say I get down to the algorithm that we'll be discussing. Yeah, before we get down to the algorithm that we'll be discussing, let me just tell you what breadth first search would serve for. Is that this is good for um, tree, or let's take graph type of problems, right? What it means is that, let's take, you have a tree with multiple nodes, right? Okay, yeah, let's take few more nodes. Yeah, if you have a cluster like this, you are asked that you are going to start from here, and then let's say we are ending here. Now you need to find the um, fastest way of reaching here, right? So how you would do that is that you have a functional or an objective that you are trying to minimize. Let's take distance, right? You're trying to minimize this. Sorry, distance. Yeah. Okay. You're taking distance to be minimized because you assume that you can move in a you can move in same velocity, right? Because of that, you would minimize distance. Yeah. So when you're trying to minimize distance, what you would do is that because of such graph type of connectivity, you would trace through the parent of this, right? You will trace through the parent of this and reach to where you had to start. And such tracks or such paths, you find that you calculate distances of all those paths, and then the lowest one is what you choose for, right? So you will have like this is also a path, but it doesn't start from here. This yeah, I don't actually have any other path. Okay, let me change my destination so that I have multiple paths, or yeah, okay, something like this. Yeah, this is a triad element here. Okay. Okay, let me keep it like this. Yeah, I start from here and here. This is my goal, right? I can go like this, or I can go like this, right? There are two paths. If this path is shorter than this one, you would take this, right? That's how you do for your Google Maps, right? So this is the entire objective. What we do is that we minimize distance. Sometimes your Google Maps give you a longer distance, but you can travel through that distance in a faster manner. Let's take it's an highway. It's a state highway, or it's a national highway where you can cruise at a higher speed. So your Google Maps, when you ask for least time, it gives you that distance or that route over any other route, which can be a shorter distance, right? And sometimes you can even ask for lesser toll. So at all those nodes, it has some attribute which we would call weighted breadth first search algorithms, right? Here, breadth for first search algorithm need not be weight, right? It can have it can also work without weights. Okay, so one search algorithm is your, I do not know how to spell this. I mean pronounce this, so I'll just write it down. Yeah. Okay. So in this, what we do is we evaluate those distances by going through a breadth scan, right? And after we have done with that breadth scan, we reassign the parent. That is based on our objective. Let's say we have to lower the distance, right, or lower the time. So those things will be there in those routes. We will be minimizing those. So let us take an example. This example was also shown in your lecture, right? So I'll take that example again, and then we'll discuss over that. Yeah. Yeah, we have a star pentagon connection, right? We have a okay, 1 2 3 4 5 6, right? We need to go to 5. We need to start at 1, right? Yeah, so let me put the connection with the distance. This is 9, this is 7. This is not drawn to scale, so please don't argue that 9 and 14 looks almost equidistant. They are not. 6, 15, 9. Yeah. So now what we do is that let's make a table. This table was not made in the lecture. So, okay. Here we need to go to the goal, right? And we'll omit the node that we are starting with. So I'm going to give 6, 3, 2, 4 and 5 at node 1, right? What is the preferred parent for all these nodes, right? So how do we get a preferred parent? Let's take 1. 1 is connected to 6, 3, 2, or vice versa. 6, 3, 2 is connected to 1. So 6, 3, 2 inherently have a parent that is 1, right? Now what we do is we measure the distance. Like from 1 it requires 14 to be here, right? um, yeah, and then 9 to be here, and 7 to be here, right? So based on the lowest count, we'll go to the second node, right? So now we are at 2. From 2, if I have to go to 3, I'll have to take 10. Since 10 is greater than 9, I'm not going to worry about it, right? Yeah. So now 4 will have a preferred parent 2, because it can have 3, but it's going to have 2 since we are in 2 now. Right? So it's going to have a preferred parent 2, and the distance of travel would be 15. Okay, 15 from here, but you will have also 7, that would be 22, right? Since you are coming from 1 to 4, right? 2 has a parent that is 1, 4 has a parent 2. To reach to 4, you require you need to travel 22 units or something like that, right? Yeah. So now we have assigned, yeah, now we have assigned our in the second iteration we have assigned the parent for other set of nodes. For 5 it is not applicable because we haven't reached to a node where 5 uh, yeah, we haven't reached to a parent node of 5, right? Let us coin it that way. Now here we'll again move to, let's take 3, right? 7, then 9, because it's the next lowest one, right? Now to reach to 4, I would go from 9 plus 11. If you see here, parent for 3 is 1, right? If I have to go to 4, I can also go from 3. The total of this distance is 20, which is less than 22. Now what I'll do is that in the third iteration, I would assign the parent of 4 as 3, right? This is the final table, right? Yeah, this is the final table. If you want to see how the table would look like, it will look something like this. All of this will come here, right? 2, 1, 3, 1. Yes. Yeah. Now what we would do, since we are done, no, we are not yet done with 3. If you see, if I have to reach to 6, now 6 can also have a parent which is 3. Let us calculate. 9 plus 2 is 11, which is less than 14. So we'll have something like 11 here. And because of that, we'll have to update our parent of 6 as 3. Right? Yes. Now, since we are done with 3, we will move to the 6th node. Right? Put 6 here. From 6 node, you can go to 5. Now we will have a parent node. This is one of the parent node of 5. And for reaching 5, you need to track from here. You see 6 would go to its parent, that is 3. 3 will go to its parent, that is 1, right? Yeah, 3 will go to 1. So that would be 9 plus 2, 11. 11 plus 9, this is 20, right? It would that would be the distance to go to 5. So here you can say that fifth node will get a parent, that will be 6, and fourth will still have 3, 2 will have 1, 3 will have 1, and 6 will have 3, right? You can do for 4 also, right? Fourth node, will not make a difference. Here you can see that 20 plus 6 would be 26, which is much greater than 21. So you will not change anything, it will remain the same. Right? This is your connectivity. Like 6, the parent will be 3, 3's parent will be 1. Yeah, 4 will also have a parent as 3, and 5 will have a parent as 6. So if you have to go from 1 to, yeah, 2 will also, yeah, 2 will also have a parent of 1. Now if you have to go to 1 to 2, you will take only one root. 1 to 4, you will take 1 3 4. If you have to go to 1 to 6, you will take 1 3 6. If you have to go to 1 to 5, you will take 1 3 6 5. Right? This is the logic behind this algorithm. Yeah, so making this table would help. Let's just strike it off. Yeah, these are not assigned yet, the places where I have given a cross symbol, right? So the other algorithm that you have is an A star approach. What happens here, you can see, is that we don't have a direction in which we are moving. We are taking the entire breadth search, and yes, you one can argue that you are going by minimum distance uh, logic, like you are going from 7 first because you are expecting if I take 1 to 2, perhaps from 2 I'll have shorter routes, right? That is not the case. Or someone can argue, let's do the hard work first, let's go from 1 to 6, that is 14, and then probably we can from after the hard work is done, maybe any other route will be easier. But you cannot go with such kind of a thought. uh, yeah, so that's why what we do is that we go with an ascending order, like we expect the best. Let's go by the shortest distance. From there, let's search our route. It is not convenient here, you go with 9, then you find that 3 is actually convenient route, and you go through that, right? So here you can say that there is no direction of movement. That's why we have another algorithm that's called A star. What you do here is that you have some heuristic options, right? And most of these options are your distance, right? What you try to do is minimize them, right? So because of that, you have a direction of movement from your um, starting point to your end point, right? So let's take an occupancy map. Okay. 1 2 3 4. Okay, let me just erase this. Yeah, 4 by 4. Right? Let's take a 4 by 4 grid, right? And some grids are blocked, right? Like your occupancy map, these are blocked. And let's take, you have a start, and you have an end. Draw a box around it. Okay, luckily it was better. Huh. Okay, now you're given with some distances um, around the place that you're going. Um, so one of your assignment has such a problem, or this was a previous run assignment. It has a similar problem like this. You're given some. So let's take, this is 0, and this is where you need to go. This is something like 4. Yeah, 4 by 4. So it is something like yeah. Okay. Uh, okay. 1 2 3 4. This is given as 4.2, and you have 1 2 3. 1 2 3. This is 1.6, 2.48, 2.48, 3.16. This is 3.16, 2.86, 3.7, 3.7. Oops. 3.7, right? So these are the measure of distance. Like if I have to go from 0 to this cell, it's going to be one distance, and from here to here, it would be 1.6. Like you'll have to come here and then take this distance, something like that. Yeah. 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 So this is the distance for traveling this way. Now, what we do with the A star approach, right, is that we have a function evaluation which is equal to the path plus the value of that state, right? So let's take, you have two connection like this. The path has a value, let's take 1.6, and the h value is somewhere around 2.4, right? You have another path which is 1.6, but the state value is 2.5. Now when you do a function calculation fn, right, at every step we take the minimum path. um, Now if you take for fn for this and this is going to be 4, and this is going to be 4.1. So you take this route and then proceed, right? So this is what we would do in an A star approach. Okay? As Yeah, so such a problem is given in, I guess, in one of your assignments, and this can help you in solving that question. So here you should be careful of choosing your heuristic values. The best one will actually lead you in a better route. So here when you see this value from 0 to 1.6, now when if you had to go a block by block, let's take something like this. If these values are 1 and 1, to reach here you would have 2, but if you are going in a inclined fashion, this would be 1.4. Yeah, this would be root 2, right? Root 2 distance. So that is what it is signifying, that there is some bias in going in the direct route rather than a staggered way or something like that. So what this method will eventually do is that it will follow a direction that is from your start to the goal until it encounters a obstacle, you can say. From there it is again going to reroute and point towards the goal, right? Yeah. So I guess these two algorithms are covered this week, and probably you can expect some assignment questions on it. And most of your assignment questions are objective, so that shouldn't be a problem. Anyway, you can always reach to me uh, on my email ID. This will probably be the last session of NPTEL doubt solving classes, and all the best for your exams. Yeah, for all of those who are crediting the course. Right? So I'll stop recording now. Thank you.